I'm Patrick. I'm a Gentoo Linux developer in my free time, and I'm an evangelist and tester of Sydbox. I've also helped with documentation and things like that. And here's my email address if you wish to contact me.
Yes, and this is me. I'm Polatel. I'm the main author of Sydbox, and I've been an ex-Gentoo developer and ex-Arbo developer. And I'm also involved with chess training, and here is my email if you want to contact me. Yes, please.
So our supporters and our sponsors, I work at a nice company called Credativ, which has been in Mönchengladbach for a long time now. We are about 40 open source experts, and we provide consulting in most things open source related, with a focus on, for example, Debian, Kubernetes. I'm in the database team. We mostly do Postgres, but we also do other things if required. And by the way, Credativ is organizing a Prox Day, a Proxmox conference, so feel free to learn more about that. And a nice thing, since last year we're an independent company again, because in between there was a lot of confusion. And Ali is nicely supported by a small startup called One More Data. And their product is basically infinitely scalable log storage built on Postgres. Infinitely in quotation marks, because we have no idea how far it goes, but the product we built at a previous company did at least a dozen petabytes without issues, and we didn't get a bigger budget, so we don't know how far it can go. So, outline, what are we doing here? So I want to give you an idea, what is sandboxing, why do we do it, what does it do for us? Which leads us to the topic of Syscall interception, because somehow we need to do this. Then that leads us to Sydbox, which I call the Syscall rewriter. Some thoughts about security and all that. A little digression into performance, and then hopefully we have some good time for questions and answers. By the way, the subtitles of the slides, since Ali did his talks with Pink Floyd, I did mine with the Beatles. I hope you can enjoy that. So what is sandboxing? So we both come from the background of Linux distribution development. So we want to usually build some software so we can distribute it. If we can't build it, we have a problem. But build systems do the weirdest things. You wouldn't believe what they do. So we need to somehow confine them and prevent this badness. So for example, there's some packages that say, well, I need a new user, let me write to etc password. Interesting, but usually not what you want. And on the other side, why would you ever read my SSH config and maybe my SSH private keys there? There's no reason to ever do that. So there's both the aspect of basically accidental and basically malware behavior. That's why we want a sandbox. Then the build environment can play around in the sandbox, and nothing bad happens. So secure. There's multiple things that end up with basically secure. So there's the aspect of safety. We want to avoid bad outcomes, accidental misbehavior. There's confidentiality, which also a type of security. So for example, your SSH keys and other sensitive data. And security, so for example, we don't want to have privilege escalation where some build system just says, oh, I'm going to install a daemon that just runs at startup because it's cool. So these are different aspects of what we call secure, but they're all very different things. And Sid tries to cover all of them with different strategies and methods. So maybe you can talk a bit about the history.
Yes, of course. And Exarbo has split from Gentoo around 2006-7, I think, and I joined Exarbo to write a better sandbox. At the time, Gentoo sandbox has many limitations, and two of them are listed here. Before network namespaces, we could restrict the builds to loopback interface, so you don't want a build to download random things from the internet, right, and such. And over time, this has evolved, and also Linux evolved a lot of new APIs with it. So around 3 years ago, I rewrote the whole thing from scratch in Rust with the purpose of becoming a security boundary rather than a simple package build sandbox. And this is what you're looking, Sid is what Sydbox 3 is, yeah.
And then basically by accident, it started growing a lot of interesting new features.
Yes.
So it moved from this basically packaging sandbox to a very multi-purpose general sandbox. So what do we need to run it? One thing is we want kernel 5.19 or later because of this seccomp feature. If you don't have that, things are a bit tricky. So it's easier to just say 5.19. I mean, it's new enough, only like, what, 3
years,
4
I
years
think,
old?
roughly, yeah. It's
If you don't have a kernel that new, then life is going to be challenging. It requires ptrace, seccomp, seccomp-bpf mostly. memfds and some other bits are really nice. There's some optional things like the landlock LSM, which are highly recommended, but technically still optional. Newer kernels add new features. Some of them are, a little bit hidden, maybe marginal, but they help. Kernel 7 also supports, for example, BPF filters on uring. So Sydbox can also now contain uring properly, which generally is a nice thing. And one thing where Ali spent a lot of brain power on is that Syd runs unprivileged, so you don't need any capabilities, SUID, or all this dangerous magic that risks creating security holes. So you can just run it as a normal user, and it should just do the thing. You could run it as root, but that's a bit weird from a security perspective. It's not wrong, it's just not necessary usually. So in this space, there are many related projects, lots of good ideas. There's, for example, the whole idea of running a full virtual machine, which is pretty heavy. So there's user mode Linux, QEMU, Firecracker, micro VMs, all this stuff. But that's extreme isolation, and it's a bit heavy. There's a more traditional sandboxes, like for example Bubblewrap, Firejail, the Gentoo sandbox, which is just called sandbox. They are mostly comparable to Syd in what they try to do, just that Syd also does a lot of things that they don't do. There's emulators like QEMU, which are in a way very similar to what Syd needs to do, but they usually focus on different aspects of the whole thing. So there's nothing that does the same thing. There's lots of things that do very similar things or a subset of the things, but I would say Syd is a bit standing alone. But all of these projects are fascinating technology. Now, how does this work? How can we do sandboxing? We have our operating system, we run some processes, and the job of the operating system is to isolate the processes from each other. And now we're saying we have a process that is somehow managing other processes. That is weird. So the interface between any process and the rest of the world through the kernel is system calls. And right now Linux has somewhere around 450, depending on the kernel version and sometimes platform, but is a lot of them. There are so many also because once a system call exists, we don't want to break user space, so processes. We don't want to break applications. So once a system call is added, we can add flags to it, we can extend it, but we can't remove it, because then all these applications would plain not run. System call doesn't exist, so I just panic and abort. Because you can't really change the fundamental nature of a system call, we have these weird things like there's clone, clone 2, clone 3, because people figured out the original clone didn't do a thing. They wanted to add it, for that they needed clone 2, and then 10 years later someone says, I have this amazing idea, now we have clone 3. We have open add 2. It looks a bit redundant, but once we have this contract with the user space, the Linux kernel refuses to remove it. So there's many syscalls we have. And a small note here, for example, Windows or OpenBSD or macOS don't have this specific weakness because you don't do system calls to the kernel directly. They put a shim in between. So the interface from the shim is stable, and what happens from the shim to the kernel is you don't know, you don't care. So they avoid this, but Linux doesn't do that. And by the way, usually the libc does things behind your back. So in your code you write open, and glibc, for example, might use open add 2 because of performance reasons, security reasons, whatever, but you never see that. So you don't really need to know all the details. You just call open and it works, hopefully. Now, there is a relatively old mechanism called ptrace, which means process trace, which is a mechanism where you can signal the kernel that you want to be notified of system calls that a process does, so you can do something with them. This was originally pretty much a debugging tool, and then someone had this idea, but what if we change what a process gets returned? We can manipulate the return value of a system call. And this allows you to do sandboxing because, for example, there's an open syscall which would work, but now it goes through your monitor process and that one says, no, it doesn't work. And while the file exists, you can't open it. So ptrace is a nice bit of machinery, but it can be a bit on the slow side. It sometimes is a bit fragile, and especially things like multi-threaded apps, I've heard rumors, are exquisitely unpleasant. So there's a newer idea, seccomp. The idea here was secure computation. We want to basically limit a subprocess to some system calls. So for example, you have an image manipulation program, it's doing some filter. The filter has some input, some output. Why would this filter ever open a file? Why would it open a network socket? So it can't. That's the original idea. There's a syscall, seccomp, which basically switches it on. So once your process does that, it can't get out. The only way out is to terminate and cease to be. So seccomp is really nice, really useful, but maybe not enough for us. So there's seccomp-bpf. So what this does is it allows you to attach BPF programs to each syscall. So BPF, that's kernel magic, that's wizard magic. The important part is this is a bytecode machine that allows you to attach basically arbitrary programs to specific things, for example, system calls. So this means we can run arbitrary code on the kernel side when a syscall happens, so we can arbitrarily manipulate them. And I think you're seeing where this goes, and now we can basically rewrite reality. A process sees whatever we want it to see. So what SID does is any process is sandboxed in seccomp-bpf. There's a thread pool of emulator threads, and whenever we get a notification, one of these threads responds to it, processes it. So this is also amazing because now there is no obvious bottleneck, and some mechanisms, if you have one single thread doing all the processing, then it limits your throughput. Here we have as many as we need, and maybe Ali can...
Yes, exactly. Historically, this was a big limitation of ptrace, that you could only trace from a single process. This means you could never easily run multi-threaded apps efficiently because you have to serialize all the system calls because they are all handled by a single process. And seccomp removed this limitation, and now we can handle them from multiple threads simultaneously. This, as Patrick says, improves the throughput and allows us to more efficiently handle system calls. Yes, this was one of the biggest changes of seccomp, we can say, to the architecture of sandboxes. Yes.
So if we look at, for example, an open system call, so one of the things we want to do is we canonicalize path names. So, for example, this path name with lots of indirection, we resolve it to a thing, to one final path. There are tricks like using bind mounts. So we can mount, for example, a root file system read-only. So whatever you do, you can't overwrite files there. And like that, a process, even if for some reason it would escape the sandbox, it's still in a sandbox. And the way this is done in the configuration is allow and deny list based on glob patterns, very similar or basically the same as rsync does. So if you know rsync already, it should be mostly familiar. And you just do things like here, allow readdir on home, which to me looks pretty understandable. And yeah, as I said, processes see the result that Sid wants it to see. We can mangle any system call any way we want, but usually we don't do random stuff. So the magic why this works is that we have a backchannel. There's seccomp-bpf. The trick here is that any seccomp-bpf rule can basically trap to user space. Basically, it sends a notification. Sid listens for that on a file descriptor, does something based on some internal rules, and sends a result back. And this means that all the heavy stuff doesn't need to happen in BPF filters, because in BPF they would be horribly complex. Like this, we can have relatively thin filters, and all the heavy work happens in user space in SID. And you might notice that now we're doing a move from kernel space to user space. Yes, there is a performance hit, but that's unavoidable for this kind of sandboxing. And here's, for example, a nice slice that Ali made. It shows basically at the top there is the open system call, and then it goes through different basically filter stages. And for example, down here, we can just, for example, hide a path, like this file does not exist, and your process will never see that file. Yes, it's there, but the process can't see it. Or we can deny access, and even if you have all permissions, because the system call is filtered, it doesn't work. And this mentions one little thing that is part of the big magic. We don't let the actual system call do the thing. There's here this seccomp-bpf thing. We are basically injecting the file descriptor into the process so that everything looks good for the process, but the system call it started doesn't really happen. So this is dark magic, but it all makes sense. I think Ali could talk hours about this.
Yeah.
And oh yeah, there's a few other things. For example, there's a crypt option. We can let SID encrypt files so that from the outside it's no longer readable, only in the sandbox. We haven't really figured out a good use case for this, but it basically gives you isolation. so that if you have a multi-tenant system, no one can read anyone else's home directory outside of the sandbox. So even if they escape the sandbox, which they shouldn't do, they still can read their files because they're encrypted. And they can't get a key because complex reasons that Ali could talk hours about.
Yes, it's hidden safely, let's say it like that.
So, security. One big issue is that we have to trust the kernel. If there's a kernel bug, there's nothing we can do. If the kernel gives us wrong information, there's nothing we can do. If there's a malicious modification of the kernel, we'll go rootkit, there's nothing we can do about it. If we get basically wrong information, then as a sandbox, we can't really help that. So we assume that the kernel is fine, and the kernel has no bugs. Well, we hope we don't hit any bugs. And anything that happens within the application is basically not our thing. We just care about the boundary of the system calls, and the goal is to be precise about basically filtering and guaranteeing that what the configuration says actually happens. So Sydbox goes to a huge amount of effort to avoid TOCTOU, time of check to time of use. That's a type of race condition where you, for example, check an object and then you think about it and you do something, and there's time between these two things. So for example, you check if you have access to the file with stat system call, then there's maybe a context switch, and by the time you open the file, a malicious actor might have replaced it. And this is one issue that has caused many sandboxes, because you can basically flip around, and if you flip hard enough, they suddenly give you access to files on the root file system that you should never see and things like that. Highly unpleasant, and that's how you break out of a sandbox. And Sydbox wants to avoid this, and does a lot of this, like what I showed, this seccomp-bpf. That is one of the methods how you make this highly unlikely. I don't want to say impossible, because maybe there's some path we haven't thought about, but at least it gets very hard for an attacker. So how this works in general is, usually we think of a path as a thing that points at a unique thing. That is generally not guaranteed to be true. A path is not a single pointer, but a sequence of things pointing at each other. And for example, this path is at least 5, maybe 6 distinct things that basically point at each other. If you walk such a path, so you have this path, you want to figure out what is the inode of the object at the end. If you walk that path, it's a snapshot in time, and it takes you time to walk the path. So if there were a malicious actor flipping a symlink really fast, and you start walking the path and you do a stat to see what is this object? Oh, it's a file. It looks good. And by the time you come to open it, it has been replaced with a symlink to etc password, and my sandbox reads your passwords. That would be pretty bad. The main thing is the object at a time of check is not the object we have at a time of use. We got confused, we got tricked, because this is not stable, not guaranteed stable. Maybe you want to...
Yes, this has been a historical problem across all sandboxes. It's not new to SID or any other sandbox, and this race condition has been As Patrick mentioned, this addFT API to inject file descriptors into processes and other things like openat2 system call allows you to disallow symlink resolution in all components of the path and so on. Linux gives new APIs such that we can do as hard as we can to avoid these race conditions. Is it completely a solved problem? I don't think so, because the nature is always there, this inherent problem that the thing may not be at the check and at time of use, right? So yeah, we do as hard as we can to avoid that, thanks to recent Linux. And this is again one of the reasons we require a recent Linux. Yeah, I can say that. Thanks.
And that leads us to Paranoia. Basically, usually we assume that applications are nice and they just do accidental things. You know, user mistyped and we try to open a path that doesn't exist. But we have to assume that that applications are actively malicious and try to break out of the sandbox. And one of the little things is that Sydbox tries to always return the right error codes as a kernel would. So from an application perspective, you should not be able to notice it because it looks like the kernel just didn't give you access. And any new or unknown system calls are blocked by default. So if you use an older version on the newest kernel, it might block, for example, IO uring, because at the time there was no support for it. So deny by default. If you don't do that, if you allow by default for a sandbox, that means possibly you open a huge attack vector, so need to be a bit careful. A lot of effort to prevent race conditions and time of check to time of use. And the whole thing is an onion design with many interlocking layers. The idea is, we hope that even if one layer fails, as a bug happens, the other layers should prevent escaping. So for example, there is this seccomp-bpf layer, and we put the whole thing in landlock LSM if we can. So even if you were for some reason able to break out of the seccomp sandbox, you're in a landlocked sandbox and the kernel still denies you. So hopefully you don't find two kernel exploits that allow you to escape. But even then, there's glue traps and self-destruct. So if by accident you somehow were able to hijack a SID emulator process, it would most likely terminate itself because something weird happened. So basically, even if you break out, you don't break out, and we hope that the number of layers is strong enough that no reasonable attacker can get out. Also, drop privileges. You know, if your process doesn't have privileges, they can't be used. So, for example, some of the threads basically use seccomp to nail themselves down, and there's nothing they can do except terminate. So even if you manage to hijack the process, well, you can call exit. Good job. And we hope that this is hard enough to hopefully motivate you to give it some stress testing. There's a capture the flag available. You can SSH to this server with this username and password, and there's a file etc.ctf. If you can send Ali the content of that file, you get, I think it's 200 euros at the moment. So, please do something. So far, there were no successful attempts. There were not that many serious attempts. It is a bit sad that no one wants to break our toys. So we're doing a lot of extra work. How bad is the performance impact? So one thing is, it depends on which component you look at. A lot of these seccomp filters run in kernel space. They're cheap. They're nearly for free. As soon as you trap to user space, it's a lot more expensive. And there's one interesting thought. We can do read and write only on things that we allowed. So since they're allowed anyway, we don't filter read and write. So once you have a file opened, read and write should go at native speed. It's only the open, for example, that might be a bit slower. Most of the overhead is on the kernel side, so there's not much we can do unless we become kernel developers, but that's unlikely. So just as an idea, this is from CI, so it's maybe a bit noisy. Like these are not perfect values, but they're hopefully good enough to show the idea. If you build Git without sandbox natively, it takes here like 104 seconds. If you run SID with the Paludis profile, which is basically the one that is used for building packages on Xerbo, with landlock, it's like 1% slower. So there is an overhead, you can measure it, but this is basically for free. And if you use path hiding, where it needs to do a bit more work on the, for example, open system call, that's like 40–50% slower. That is noticeable, and there's not much we can do about that. So if you don't need this feature, maybe keep it disabled, then the rest is for free. To compare that, GVisor, which does roughly comparable things here, has an overhead of like 300%, which is a bit sad. So relatively, SID is relatively efficient, not perfect, but most of the time you shouldn't notice it. And if you have Intel hardware, the performance you lose on mitigations every year, that's a bigger hit than SID, so it's still for free. So profiles. To make it easy to run specific things, you can run SID with a profile, which is a config file with specific rules. And it can, for example, contain checksums of binaries, so you can only execute binaries that are in this list with a checksum. So even if an attacker were able to execute arbitrary code, they wouldn't be able to exec anything. So the usual shell code just doesn't work. And the profile, of course, can enable or disable features, and pretty much most features are optional and can be disabled, and it's always your choice if you want or need these features. To make writing profiles easier, there's a tool called Pandora. And once you open Pandora's box, everything is weird. It runs Sydbox in permissive mode, where it doesn't block anything. It just gets a log of events, and out of these events it tries to generate a config, and it tries to do things like if there's this many accesses to a directory, to specific files, it tries to use a wildcard for that whole directory. So maybe it's not exactly what you want, but it's configurable. And for example, I could run here Pandora profile wc-l dot, like I just want to run something, then I get a profile, and then I can run the command with SID, and now the command is contained and hopefully cannot break out. And then you get a file that looks something like this. So you see there's a read dir on a directory. That's why I ran that. There's the command I ran and its dependencies. And you see, for example, there's reading etc ld.so.cache. So there's all kinds of interesting things you discover, what files are needed to just run a simple command. And then there you see the truncated checksums. I truncated that because it gets a bit too long. But like this, if you try to run anything else with this profile, it's just going to not execute. Like, this is not an executable file, go away. Which is pretty nice. And within SID, there's another funny thing. There's a virtual device node, dev SID, and through this device node, you can basically set any configuration item, and it has different modes, so you can basically lock it, so the config cannot be changed. And this, in theory, allows an application to, let's say you run a database and you run out of disk space here, you want to add a table space to put stuff there, you would need to restart it to add it to the config, but we can do that at runtime. So in theory, your process can adjust the config within certain limits, and once it is happy, it can disable further changes, and then it's frozen and can never be modified again. So for example, this can be used to do some startup initialization stuff, and then you drop as many permissions as possible, lock the sandbox, and now you're as locked down as it gets. So this is very interesting for daemons and long-running services, but so far we haven't really seen any interesting use of this. So please experiment, do interesting things. There are some bonus features. For example, it's a container runtime. What is a container? Well, it's basically a sandbox, so why not be both? There are some funny things. For example, segvguard, it's a rate limiter, so if a process crashes, which can be a sign of someone trying to exploit it, it keeps track of how often it restarted over time, and it delays execution if this limit is reached. So the usual, for example, ASLR leaks get really hard because now you have a rate limit. There's IO control sandboxing, so you can use, for example, CUDA and ROCm. It's a little bit quirky, so it's not really easy to use, but we have run OpenCL programs within SID, and they're properly sandboxed as far as we can tell. There's path hiding, so things that exist are not there. Path masking, you can rewrite path, and no, this directory is actually that directory, if you want. And you can do append-only files, so we could contain the logger, so it can only append to files, and the kernel ensures that. And the logger can never remove or edit any existing data. It can only append to files, which means the system logger would be extremely hard to manipulate. Very nice for forensics. Network sandboxing, of course. And I guess safe set ID and ghost mode are your specials.
Yes, safe set ID is a way to make SID drop user with the sandbox process. Imagine you're running nginx or such. It will bind as the root user and it will drop permissions to a lower HTTP user. And with running under SID, we can also make SID drop the user with it. So it's as a supervisor, it's always close to the process. It's sandboxing. They are always sharing the same user. And this way you are also preventing a stray process from changing the user in a way you didn't define. You can also say, for example, I want this process to change from root to nginx and this only. And SID will do the same with it. Ghost mode is another one, which is like the very paranoid confinement, like Patrick explained with seccomp mode, the initial mode earlier, in which case we separate SID from the process, and SID stops doing any handling and all system calls will get denied. This enters the process into a very well-confined mode, in which case it can do not much besides reading and writing, like the basic seccomp idea. These are more added hardening features you can use optionally, not on by default. Yeah.
And there's many other things we don't really have time for, so please feel free to read the documentation. It has many references to technical documents and things like that, so might be an interesting read. And that's basically the end of our talk. I could try a small live demo if you want, or we can skip to question and answers.
I think we still have 15 minutes, so
okay.
I think it's
then
time that do a live demo, and afterwards we use the remaining time for the question.
So what we try to do is, this is the directory where I built the slides. That's a PDF generated from Tech. And if we run Pandora
profile.
Oh, wait. Pandora. So if we just run a profile with the default settings, oops, it already exists, go away you file. It does a thing, and you see here the files that were used in checksums, but if we look up there, make somehow got terminated, bad system call. What happened here is that this is using Lua LaTeX, Lua JIT. Lua JIT kind of upsets SID, so it just denied. So we can really use this directly. We need to tell Pandora to allow unsafe exec memory. I mean, we have a just-in-time compiler, please don't kill it. And the -L100, we found a little bug in Pandora. So this is just making it not explode violently. And again, we need to remove the file, and now it's compiling the PDF, which takes a few seconds. This is now running within the sandbox in permissive mode. So the sandbox shouldn't do anything. It should just log all the things. And there you see generated 368 SID rules. And that's nice. So how does that look like? So it does a bit of comment when and where it was generated. There's allow file systems. You can even suppress file systems. You can say, I never want to access a squash FS, so don't go there. And as you can see, I'm using ZFS on this machine. Then here at the top, you see the directory it was run in. And you see this 3-star glob. That's basically this directory, any directory under it, any file. Then we have here basically there's here varlib techmf. Interesting. That's all the libraries and things that are needed. Here's some config. It needs to read etc techmf, it needs to read user share something. That's all the bits that tech uses, right? Allow create pipe. Yes, make is using pipes, so we need that. And here's something that surprised me a little bit. Something is calling find. Okay, that's nice. So you can use it to audit and maybe find unexpected things like this. It's not really unexpected, but I thought, I called make, I didn't call find. That's nice. And yeah, here's more. You have the .techlive directory, and it's reading different fonts and lots of stuff. And it also needs some I/O controls. So these are the only ones it has seen. One downside of learning mode is that if you don't exercise a code path, you maybe don't get all the system calls or all the flags you need, and it's too restrictive. But this is at least a good starting point for writing a more comprehensive policy. And here it turns on landlock, and these are the landlock rules, which are basically the same files, but we have two different layers of sandboxing, and hopefully that is good enough. And it's basically the same files, just in a different context. And here you have all the checksums. So if you use this profile to run anything else, bad stuff should happen. So now I want to just run make clean. And if I, for example, take this. So because my notebook doesn't have landlock LSM active, but SID creates the rules, we just override it here. And we just say, hey, make me a PDF. Actually, how about I just do ls? Oh no, permission denied. With this profile, obviously, I'm not supposed to run ls, so it tells me to please not do it. But I can make PDF, and that is interesting.
Yeah.
It's triggering another code path.
Yes, yes.
Let me see. I had a saved config because this tends to go weird. And now it runs. So getting the profiles right is a little bit tricky, especially things like make. If you run make clean, for example, you have a different view than if you run make and run make again. So it's very easy to have incomplete profiles. And yeah, it finished. And now we should see there is a PDF, and yeah, it is there. So this worked pretty okay. So, do you have any questions or comments or ideas?
I didn't fully understand what is the difference to Linux, maybe in combination with an container engine.
It works on a so Linux tries to solve a slightly different problem, and it cares more about confidentiality. So it's more about we have multiple users on the system and they run in different privilege levels. So someone who is in top secret level can read top secret, but someone who's in civilian status should never be able to see top secret. So Linux has this whole machinery with transitions and all this, so that basically we can somehow express this user belongs to this class, and these objects belong to this class, and this class may read objects of this class. That's something that SID doesn't really care about. It cares more about things from the perspective of a traditional container engine, but it adds a lot of extra paranoia. So if you run standard Docker, for example, it had weird exploits where, what was it? If you made def null a symlink, I think?
Yes, that was yeah.
If within the container def null was a symlink, bad stuff happens. So it's good at like preventing accidents, but it's not a hard security boundary. And SID is basically a container engine in the widest sense with extra paranoia. And so what Ali, for example, tried and succeeded is you can run Firefox with, for example, video acceleration in Sydbox, and it will never be able to read your SSH key. So even if some malicious website somehow triggers an exploit within Firefox, it still can read your SSH keys, so hopefully you can worry a bit less. But it is a very different layer of this whole machinery compared to Linux. And in theory, Linux shouldn't interfere with SID in any way.
Yes, you can use both. There is no problem in using both. Linux is in fact more of a systemic approach to secure the whole operating system, right? But SID focuses on a process itself that it contains mostly. So they do different things, but you can use them together with no problems. Yeah.
Other questions? Actually one. It reminds me a little bit on the pledge mechanism of OpenBSD. Am I guessing right that this was a huge inspiration for this?
Yes, this is true, and we also use many category names similar to OpenBSD pledge, so people using pledge can also switch to Sydbox easily. They are very similar. OpenBSD has the advantage that they can change the kernel and the user space with it, but SID has to be in Linux, so it's a much more scope project, but we have taken many inspiration from pledge and unveil. Yes, thank you for the question.
Okay, I see, thanks. If nobody else has, we have a
BPF is not compiled, is it?
So BPF is a bytecode, and usually you write not like the binary bytecode, but a language that looks a bit like C. and that gets compiled. And on top of that, there's a verifier. So BPF, for example, has limitations. It doesn't allow backwards jumps. It only allows forward jumps, so that you can't have infinite loops. Because this runs in kernel space, you don't want to have infinite code, like an infinite loop that would block at least the CPU, if not the whole kernel. So BPF is like the way you usually write it. It looks like C, like a subset of C, but it is quite different.
I'm thinking the overhead must be big then. If you do a lot of short syscalls, the overhead.
No, in the end, the expensive thing is switching from user space to kernel space, because you need to save context and lots of things. So that takes a few thousand CPU cycles. And then the BPF probe attached to that takes dozens, maybe hundreds of cycles. I mean, depending on how complex it is. People wrote whole databases in BPF, so that is big. But what we're doing here is basically either we just deny a system call, so this is basically one operation, so that's fast, or the bigger stuff needs to trap to user space, use the mechanism I mentioned earlier, and that one is another context switch, so that is expensive, but the actual BPF part is surprisingly efficient. And the benchmarks, wait up. So most of the time you don't spend in system calls usually. So something like Git, I would guess 10-20% maybe of the whole time are system calls. And there's like a 1% difference. So it makes system calls, I don't know, 10% or so more expensive. If you're running something like a web server that's doing a lot of system calls under high load, I think you're going to notice, but for most applications, like for Firefox, you spend most of your time in user space, so the system calls are not a substantial part of the whole thing. So most of the time you shouldn't notice.
Yeah.
Fine. Any other questions?
I want to add a little comment. We mentioned OpenBSD. Some of the mitigations are also inspired by, for example, hardened BSD, FreeBSD. So they're all full of great ideas. And Ali took a lot of their ideas, experiments, and tried to build them in Linux. So
Yes.
Pretty cool.
Yes, and we are also working together with hardened BSD guys to get some of the SID mitigations to hardened BSD and over to, so share the love and make it bigger. Yeah.
Then have a nice evening. Have a nice remaining FrOSCon and safe travels, everyone.
Thank you very much.